Okay, I think we can start with the introduction. So, welcome back, I would say, to the machine learning webinar series of 2025. And today I have the pleasure to introduce Professor Michael Shield, or who we will give, or I will give a small introduction about his achievement in a few minutes. And I would like just to remind you that this is the following up of a machine learning school that has been conducted in Turin, in Italy. We were very pleased about the response to the school. We had more than 250 participants for 42 countries, and it was a wonderful experience in person, and I hope also online. We received a very positive feedback, and as following up to the school, we have this series of distinguished scholars from the field of applied machine learning or theoretical machine learning, more the applied side, that where we started the last time with the Professor Karnidakis, and today we have the pleasure to have Professor Michael Shield from Johns Hopkins. A reminder, the series is composed by 6 keynotes, and today we will use, as always, the platform Cassini. So you might be connected here or either through Cassini or either through Zoom. I think most of you through Zoom. And the rules are as follow. We will leave the presenter the time to show us his presentation, but you can ask a question in the chat, and then in the following up section, the question section, we will grab this question and directly or select some of this question and ask to the speaker. Finally, I would like then to introduce, before giving the stage to Professor Michael Shield, I would like to give you some introduction to his career. So Professor Michael Shield is at the Department of Civil and System Engineering and holds a secondary appointment in the Department of Material Science and Engineering, and is a fellow of the Hopkins Extreme Material Institute and a member of the Data Science and Artificial Intelligence Institute. His research focuses on uncertainty quantification for a wide ranging problems in computational, ranging from computational mechanics and computational material science. His group, known as the Shield Uncertainty Research Group, conducts the research in uncertainty quantification, applied machine learning, and stochastic methods to better understand the effects of uncertainties and random vibration on the performance of material and structure. I personally believe that it's very important that we have in this seminar an uncertainty quantification point of view and the cross-lapping between these two disciplines. There is probably no better person than Michael Shield that can provide such a presentation. His group, in fact, also developed an open source platform named UQPy, Uncertainty Quantification with Python, which I highly recommend for whoever has to deal with uncertainty quantification problem, both forward and inverse. It includes many techniques from this field, including also, of course, machine learning approaches, and some, as I can just name a few of them: polynomial Gauss expansion, Gaussian process regression, neural networks, and a lot of many Monte Carlo methods. Professor Michael Shield, despite his young age, has received many different funding from prestigious foundation, and he has also received already a large number of quite important award. The last that he received is the Early Achievement Research Award from the International Association for Structural Safety and Reliability in the last conference in Los Angeles, ICOSR 2025. It also received the Department of Energy Early Career Award, NSF Career Award, the ONR Young Investigation Award, and the Yassar Early Achievement Award, and many more awards that will come in the future, and I'm pretty sure. And he, since 2011, he has wrote more than 80 papers published in peer-reviewed academic journals. And knowing Michael, these are very high-quality papers, as I know that this work always has focused more on quality than quantities. And finally, I would like to give the floor to Michael Shield and say thank you one more time to be here with us today.
Wow. Thank you, Marco. Very kind introduction, and so nice to be here. And I thank you all for your invitation. I'm going to go ahead and try to make sure I can share the screen here, make sure this works. Bear with me for just a moment. And so do you see the presentation or do you see my notes view?
No, the presentation.
Okay, great. Yes, thank you again. Really, truly a pleasure to be here. I can't thank you enough for inviting me. This is really a wonderful opportunity to share some work on UQ and the intersection of UQ and scientific machine learning. And what I'm going to try to accomplish here, I'm going to talk in two parts. I'm going to try to kind of balance between being somewhat tutorial in what we talk about, how we introduce uncertainty quantification and scientific machine learning, but also then how we can use scientific machine learning to solve problems in uncertainty quantification. Before I get started, I need to acknowledge many people. I'm not going to call everybody out by name here. But everybody you see here has contributed to this talk in really important and substantial ways, and you'll see their photos flash through the presentation as I move forward. I also need to acknowledge the support for this work. Most of the work that I'm presenting here has been supported by the U.S. Department of Energy and the Defense Threat Reduction Agency of the United States. And so without that support, this work wouldn't be possible. I'm going to start the presentation with a couple of short advertisements. So the first one is that within the last, I guess, 9 months or so now, I've introduced this course, Introduction to Uncertainty Quantification on Coursera. So this course is really intended to be for beginners in uncertainty quantification. So we talk about the nature of uncertainties in models, probabilistic, basic probability, how we propagate uncertainties, and then we get into a little bit on some, more advanced topic, polynomial chaos expansions and reliability and sensitivity and so on. So if you're interested in, really getting started in UQ, this is, I think, a great way to do it. The other advertisement, which Marco also already kindly introduced, is the software UQPy that my group develops. UQPy is a collection of Python modules, and the way I like to describe it is that it's not just a toolbox for UQ, but it's a development environment. And so it's built in a very modularized way that allows for the ease of new methods and new approaches to be implemented. We have a couple of papers, actually 3 papers now on the work, and we've got contributors from all around the world. It's public, it's open source. Everything is available on GitHub. You can download it from the Python Package Exchange. We have thorough documentation, many examples. And most recently, I'm happy to announce that we've built this, what we're calling the Scientific Machine Learning Module, or SMILE, as we affectionately refer to it, which is built directly on top of PyTorch. So it seamlessly integrates with PyTorch to let you do things like integrate Bayesian layers and probabilistic dropout and various other things that enable UQ in neural networks. And you can find more about this on this Software X paper that was just published over the summer. So with that said, with the advertisements concluded, I would like to dive into the technical piece. And I want to start in this first part by talking about how we perform uncertainty quantification in scientific machine learning models. And so, again, I want to start at the basics. And so I want to start by talking about what we mean by scientific machine learning and putting that into context, and specifically what we're going to be interested in here. So scientific machine learning, broadly speaking, is at that intersection of ML and physics-based modeling, right? And there are a variety of topics that we can think of when we think about scientific machine learning. We can think about things like PDE solvers, which I'm sure you heard all about with George Karniadakis in the last presentation. Um, and things like pins and various other methods. You can think about PDE discovery. So this is talking about symbolic regression and things like Cindy and those type of approaches. What I'm going to focus on here is this class of methods that are called operator learning. So in operator learning, what we're trying to do is learn a solution operator, usually for a PDE. And to give you kind of a brief introduction, and again, maybe many of you have already seen this, certainly with Professor Karniadakis' presentation last week, I'm sure he touched on these, but the idea with operator learning is that whereas classic regression type methods are working between vector spaces, what operator learning aims to do is learn a transformation or an operator between continuous function spaces. So we start with some input function. We have an operator, usually a PDE, that operates on that input function and produces some output function. Now, I want to be careful here because I'm going to try my best to be consistent throughout this presentation with notation. So you'll see here, for example, that we're looking at an operator G that is acting on an input function U and producing a solution S. I'm going to try to be consistent with that, but I won't be consistent throughout because I'm pulling from various sources and sometimes the notation changes. I'm going to try to be diligent and careful about when I change notation, but to the extent possible, I'm going to try to be consistent. So you can think of an example where we have a simple PDE here with some initial condition U of X, which is our input. And then the operator, which is that PDE, is trying to map that initial condition on the input space to some solution in space and time. And I'm going to specifically focus on two classes of operator learning. One is the very well-known deep operator network, or the DeepONet, which is derived from the universal approximation theorem. So the universal approximation theorem for operators says that if we're given some general operator, we can build a neural network that will approximate that operator to within some specified level of accuracy. And if we look at this and break this down, what Professor Karniadakis and his group kind of recognized is that you can create this architecture with a pair of neural networks, one which we refer to as the branch net and one which is referred to as the trunk net. Now, the branch net takes the discretized input, so we have to discretize our input. That's going to come into the branch net. And then the trunk net is going to identify or learn a basis that spans the output space. The dot product of the outputs of those two neural networks gives us the solution operator. The second is again, very well-known Fourier neural operator. And the way the Fourier neural operator works is it aims to approximate the convolutional kernel integral. And so it does so by mapping from first lifting into a feature space and then performing a series of Fourier transforms in Fourier space and operating on those Fourier transforms and then mapping back down to the solution space. So these are the two classes that I'm going to focus primarily on. But I want to kind of take even a step back from this and sort of look at the bigger picture. And I want to do that in the context of what are widely being referred to now as foundation models, right? So most people, when they think of foundation models, they're thinking about ChatGPT and the large language models that are so ubiquitous now. But if we take a broad view of what a foundation model is, right? A foundation model, if you just look at what Wikipedia is, a machine learning or deep learning model trained on a vast data set so that it can be applied across a wide range of use cases. And so I'm going to actually lump many of the scientific machine learning models into this category, scientific machine learning or scientific foundation models, as some people call them. But with foundation models, we aim for certain characteristics, right? These are really big models. We want to make sure that they're generalizable, right? So for large language models, we have to be able to perform multiple tasks. In scientific machine learning, maybe we want to tackle multi-physics problems, right? We want to be able to tackle really large and complicated and generalizable problems. We want them to be adaptable, right? We want to be able to fine-tune them so that they can adapt to different domains. So if we're thinking again about scientific machine learning models, we want to be able to apply different boundary conditions, initial conditions to different geometries and so on. And lastly, we want them to be extrapolatory, right? We want to be able to take them to regions where we haven't necessarily trained them. Of course, all of this is aspirational. This is what we aim for with a foundation model. But in scientific machine learning, what we want to be able to do is we want to be able to make predictions in space and time based on the underlying physics that the model's been trained on. So I want to talk a little bit about the components of foundation models. And these are going to become important when we start talking about uncertainty quantification in this landscape. So the first, which many people don't think of when they think of scientific machine learning models, is this idea of tokenization. So tokenization is well known in the large language model community, right? You have to take a language and you have to break it up into a dictionary of discrete, sets of letters and sounds and so on. So you split words into smaller units and you define a dictionary. The analogy that I make for that in scientific machine learning is that you have to discretize your domain, right? You have to take your complex domain and you need to discretize it in space and time. So those are sort of analogous, what I'll refer to broadly as tokenization for foundation models. The second are the learning objectives, right? So what are we trying to achieve when we build these models? For large language models, maybe we're trying to predict what the next sentence should be, or we're trying to answer a question that's been posed by a user. In scientific machine learning, this is typically some sort of regression, or as I've talked about, operator learning task, where we're trying to learn the solution in space and time. The next is how we actually build that model, so the model architecture. In large language models, this is almost always transformer-based. You have encoder-decoder models. You have some decoder-only models like ChatGPT. In scientific machine learning, there's a lot of transformer-based models. I'm not going to talk a lot about transformer-based models today. I'm going to talk primarily about this class of function or class of methods that I've already referred to as neural operators. And finally, we have the training component of this. So training is all of the vast data sets that you're going to build in scientific machine learning. That might include simulation data from numerical models. It might include experimental data and the integration of that huge amount of data to be able to train the model and learn. So to give you some sense of these are really, really large models, and the size of the models is really critical for generalizability and for being able to consume large amounts of data and train. So we look at large language models. You have the famous ones like Google's BERT, which is on the order of 100 to 300 million parameters. If you get up to the GPT and the Llama models, you might have 100 to 400 billion parameters in those models. In scientific machine learning, again, you have transformer architectures that have millions to billions of parameters. So these are huge. The neural operators tend to be a little smaller, although those are getting much larger as well. FNOs might be on the order of 1 million to 10 million parameters. Debo nets historically have been smaller, 100K net, but some pushing up to 5, 6 million parameters themselves. And then some you have these sort of hybrids like the forecast net, which is an FNO with a transformer. So now when we want to talk about the UQ in these models, the reason that I went through all of that detail about how we break down these foundation models into their components is because we need to think about all those components when we think about UQ, right? So in UQ, we need to understand uncertainty in the model, right? So this is uncertainty in the architecture itself. Like there are many ways to architect a scientific machine learning model. So we have some inputs going into a model, we have some outputs again, as I've already mentioned before, but there's a question of architecture. Within that architecture, we have a number of parameters. We want to quantify the uncertainty in those parameters. We have uncertainty in how we perform tokenization, right? What is the dictionary that you're using? What is the discretization that you're using? And what uncertainties does that introduce? And we'll talk a little bit about this as well. You have uncertainties associated with the learning objectives, right? So whenever we define one of these models, we define a loss function. That loss function may capture some things really well. It may capture other things not as well. How do we understand uncertainties in the loss landscape? And finally, how do we handle uncertainties in the training strategy, right? So we have to split testing and training data. We have to curate and select the data that we're going to train on. We might do a very large pre-training and fine-tuning on, a specific subset of specialized data. There's learning rates and learning schedules that we have to, that can introduce uncertainty. So all of these factors come in when we talk about UQ for foundation models. And we can look at that through the lens, if we think of it probabilistically, of essentially what boils down to the law of total probability, right? So what I'm interested in here is I'm interested in the probability of the solution given the inputs, U, and the associated data that I've used to train the model. Now, this is a long integral, and I don't want to get into every single piece of this, but all of those factors that I've talked about, tokenization, loss function, parameters, etc., factor into this law of total probability in quantifying uncertainty in these models. What I really want to focus on is this second term here, which is the uncertainty associated with the parameters, given that I've selected a training data set in a model form and so on and so forth. And that is going to be a really critical component of this because, as I talked about before, these models are huge, right? We have millions to billions of parameters. So this probability, quantifying this probability is really, really difficult. And if we look at it, we can actually break this down using Bayes' rule. And so we can define the probability of the parameters through Bayes' rule through the likelihood of observing the data, given all of our models and so a model and training and so on and so forth, times a prior on those parameters. Okay, so this is, it looks complicated, but this is really just Bayes' rule in action. And so I'm going to simplify that because that notation gets really arduous. I have a lot of terms there. I don't want to use all of that notation. So I'm going to simplify things and just say, okay, we're going to use Bayes' rule to quantify the uncertainty in the parameters theta given the data D. The rest of those terms are sort of implied here, okay? Now with that, we can define the predictive probability of the output. Again, this is just a very simplified form of the equation that I showed on the previous slide. And when I take this equation, I can then get the expected value for a prediction at a new point, or I can look at the variance of the prediction as a measure of uncertainty. And through the law of total variance, I get an expression that looks like this. Now, the important thing here that's interesting is that when I apply the law of total variance, you can see that the components of the variance split, and actually those are nicely interpreted, where the first component is our aleatory uncertainty, right? So that's the uncertainty associated with randomness and noise in the data itself, and the epistemic component. So the epistemic component is the insufficiency in my model, it's the lack of training data, and so on and so forth. And I can split these components, which gives me a really nice interpretation in a Bayesian neural network. So how do we actually tackle this problem? Well, the sort of naive approach would just say, okay, well, this is Bayes' rule. Let me go ahead and, I'm going to throw Markov chain Monte Carlo at it. So if I try, just simple random walk Metropolis Hastings, um, I'm going to fail, right? Because random walk Metropolis Hastings is not going to work in a million dimensional parameter space. We would need exceptionally long run times. We'd have very high rejection rates, and it doesn't scale to those type of dimensions. We can do better with methods like Hamiltonian Monte Carlo. So in Hamiltonian Monte Carlo, what we do is we define the state of the system as the position of a particle in an energy landscape. And to do so, we define this sort of fictitious momentum. So you have the position Q, which is the state of your system. Then you have this momentum P, such that the particle's dynamics follow Hamilton's equations. And that's what I'm showing here. And then you can define the energy landscape by defining the probability distribution in this way. So pi is the probability distribution you're trying to sample from. That's the posterior of the parameters of my neural network. And then I can evolve the system by defining the potential energy and the kinetic energy in this way, and then solving numerically using a symplectic numerical integration scheme. I can propagate this and draw samples. Hamiltonian Monte Carlo is great in many ways. It has a very high acceptance rate, but it has some drawbacks as well, right? It requires time integration, and you need to compute gradients of your likelihood function at every step for that time integration. That can get very expensive and can also have trouble scaling in dimensions. So one thing that we've done is we've looked at how we can incorporate pins actually to speed this up. So in this case, we looked at what are called Hamiltonian neural networks. So you take your position and your momentum, and you aim to use a neural network to predict those derivatives so that you can compute Hamilton's equations. We can build a physics-informed neural network that will do this by using an in-graph, your typical in-graph gradient for pins. And this is a neural network that will automatically satisfy Hamilton's equations, and we can apply this in the context of Bayesian inference, right? So a few years ago, we wrote this paper about how you can do Bayesian inference by training Bayesian Hamiltonian neural networks in the context of Hamiltonian Monte Carlo for Bayesian inverse problems. Now, this is a nice development. It scales to maybe hundreds of dimensions, but it does not get us to where we need to be for Bayesian neural networks. So we need to go to different strategies, right? This doesn't quite get us where we need to be. I would say the most common approach when parameter spaces get really, really big is to use what's called variational inference. And so in variational inference, we're going to approximate the posterior. So we're going to approximate, our posterior distribution of the parameters by something that's simple and tractable, right? We're going to denote that by Q sub alpha. And what we're going to then do is we're going to try to minimize the difference between the posterior and our approximate distribution. And there are a number of ways that we can do this, usually by defining some divergence. The most common would be using the KL divergence, the Kullback-Leibler divergence, using a method that's known as Bayes by backprop, but you can also use other divergences as well. So if we use the KL divergence, it's defined in this way. And what we really want to do is we want to minimize the KL divergence. So we define a loss function like this. When we apply Bayes' rule to this expression, we can break this down into a computationally tractable loss function where we need to compute the KL divergence between the between our approximate distribution and the prior. And then we have this expected log of the expected log likelihood. This is what's known as the evidence lower bound, or ELBO, which is the common approach for variational inference. And what this aims to do is really say, okay, I'm in this space, which is this sort of blue area that covers the space of distributions that my approximate distribution can cover, and I want to find the one that is closest to my true distribution, which doesn't live in that space, right? In reality, we usually apply some factor lambda to this, but I'm not going to get into those details. So the Bayes by backprop algorithm itself does this exactly. You're minimizing the elbow under the assumption that your simplified distribution is uncorrelated normal distributions over your parameters. In this way, the first term becomes analytic. We can compute the KL divergence analytically because we're working with normal distributions. And then we can use Monte Carlo simulation pretty easily to estimate this second term, and things become quite efficient. Now, if we look at these sort of approaches in the context of Bayesian neural networks, they have various advantages and disadvantages, right? So if in an ideal world, we would use something like Hamiltonian Monte Carlo for all the problems that we can, but the problem is that those are computationally very expensive and they have trouble scaling to very, very high dimensions in some cases. VI, on the other hand, is computationally efficient, right? All I really need to do is solve for the mean and standard deviation of my parameters, which makes it comparable in training costs to conventional neural networks. But it has trouble with some of the uncertainties. It's not quite well understood how reliable those uncertainties are, and in many cases they're not reliable because you're making very simplifying assumptions, you're ignoring correlations, you're making assumptions on Gaussianity, and so those methods have trouble as well. Another popular method is the Monte Carlo dropout. I personally am not a huge fan of Monte Carlo dropout. What it really is doing is defining a Bernoulli distribution on those parameters and dropping them out. And in our experience, it doesn't work particularly well in many applications. So just to give you kind of a quick example of what this looks like in a neural network application, here we have this is not a neural operator, this is just a convolutional Bayesian U-net, where we have some input microstructure and we aim to predict under uniaxial loading what the stress field will be in that material based on the uncertain and random microstructure that's provided. We can then, using this Bayesian neural network, we can predict not just what the stress field will look like, but the uncertainty in that stress field as well. And we did a sort of benchmark between Hamiltonian Monte Carlo, the Bayes by backprop, this variational inference method, and Monte Carlo dropout. And what we see is, of course, the Hamiltonian Monte Carlo is sort of our gold standard, right? It gives us the best estimate of uncertainties, and you can see that here in the bottom right. This is sort of our benchmark for what the uncertainties look like for a given microstructure. And we can compare that with the Monte Carlo dropout and the Bayes by backprop. And what we see is that the Bayes by backprop actually does a reasonable job at estimating those uncertainties from Hamiltonian Monte Carlo. Monte Carlo dropout doesn't do nearly as well, and its uncertainties are not well calibrated to the what we're calling the sort of ground truth Hamiltonian Monte Carlo. This was published in a recent paper where we looked at Bayesian neural networks for predicting large full field material responses. But that's just applying sort of vanilla, the off-the-shelf approaches. I want to talk about how we can advance these approaches because we need, this model that I showed here, this Bayesian U-net, it's a decently large model. If my memory serves me, I think it has something like 13,000 parameters or something like that. So it's a decently large model, but we're not getting to these foundation models at this point, right? So let's talk about a few advances that can hopefully push us in that direction. So looking at this variational inference context, the question is, well, okay, so if we want to work in VI, can we improve the uncertainties that come out of VI? One way of doing that is using different divergences, right? So the KL divergence has a tendency to concentrate the uncertainty around dominant peaks in the distribution. It doesn't do well with multimodal distributions. So we can look at things like the alpha divergence or the JS divergence, the Jensen-Shannon divergence. In this case, we use the alpha divergence. But we also recognize that variational inference methods are very sensitive to initialization. And so if I take the Bayes by backprop algorithm for a very simple function here, what I see is that if I initialize it differently, I get very different solutions for this interpolation region, right? So here I have this sort of smooth interpolation, here I have this sort of stair-stepped interpolation, and all I've done is change the initialization of the parameters. Now, that doesn't look very good when I compare it to my benchmark, which is a Hamiltonian Monte Carlo here on the bottom right. And so what we did was say, well, okay, what we can introduce is this idea of ensembles as well. And so if we take an ensemble of these models, recognizing that each of these ensembles is going to be, is going to give us a better or worse fit, then we can take this ensemble and compute model weights. So each of these models has an associated weight with it that's defined through this expected log pointwise predictive density. And then we can define the posterior prediction as a weighted average of those models. And using that approach, you can see now on the bottom left graph here that we do a much better job using variational inference at approximating the true uncertainties from our Hamiltonian Monte Carlo. So this, this strategy gets us somewhere in terms of being able to improve the efficiency and the robustness of our uncertainty estimates, but it also introduces some aspects of uncertainty in the model weights, right? These model weights are actually giving us estimates through ensembling of the model uncertainty, the model form uncertainty, right? Some models are fitting better than others. I want to make a brief aside here because I did talk about tokenization, and that's what's defined here by this T, or the discretization in the case of neural operators, and talk about a method that we introduced that looks at resolution dependence. So the dependence on how you tokenize in a neural operator. So in a typical neural operator, in most applications, what we are looking at is we have to fix the input functions at specific points, right? So every input function I have has to be discretized at exactly the same points, right? And that can be problematic if I have complex geometries, if I have different finite element meshes, if I have different schemes that I'm using to solve, maybe multi-resolution or multi-fidelity type of approaches. And what I really want is I want to be able to discretize the input at arbitrary points and use that as input. So the way that we've approached that is, rather than taking the input function and discretizing at a fixed set of points, what we do is we perform a projection of those points onto a continuous function space and use the projection onto that function space as the embedding for our branch net. And in that way, we can accommodate different resolutions and different discretizations in the input. Now, I'm not going to talk about how this specifically gets into uncertainty quantification, but what I will say is that methods like this will allow us to alleviate some of the discretization dependence and the uncertainties associated with discretization and the quote-unquote tokenization in neural networks and neural operators. But let's get back to the task at hand, right? So we're trying to, again, advance Bayesian neural networks. So now I want to talk about this idea where we can merge the strengths of variational inference and our baseline or our benchmark Hamiltonian Monte Carlo. And the idea, the basic hypothesis that underpins this is that we have this huge neural network with many, many, many parameters, right? But not all of those parameters are contributing in substantial ways to the uncertainty in the solution. And what we really want to do is we want to find those parameters in the network that are contributing substantially to the uncertainties. So what we do in this approach is we start by applying variational inference. So we learn the posterior distribution of the parameters using VI. So this is just your typical Bayes by backprop or alpha black box, pick your poison. We then rank the parameters according to a sensitivity score. This sensitivity score tells us how important is this parameter for uncertainty quantification purposes. Those parameters that are determined to be less important, we just freeze those parameters, treat them deterministically, and then we're going to focus on the most sensitive parameters using Hamiltonian Monte Carlo. So what this looks like is we can compute these sensitivity scores by first taking a Taylor series expansion and taking the Taylor series expansion of each of these parameters. We can compute the variance based on that Taylor series expansion. This is what's commonly known as the delta method. And then we take the average variance contribution for each of the parameters over the training data. So what we're doing here is we're taking, this is the contribution of the variance for each parameter individually, averaged over all of the training data. Okay? So this gives us a sensitivity score for each and every parameter in the model. And these can be computed quite readily using automatic differentiation. And so the number of training parameters that we need is then defined by a sensitivity threshold. We say we're going to keep the number of parameters that satisfy some threshold of sensitivity for our model. So if I, again, look at this really simple model, I have a simple sine function where I've deliberately left out some data here in the range, near the origin, so that if I perform variational inference on this, VI doesn't perform particularly well. It doesn't give me very good uncertainties in this range near zero. Now, if I use Hamiltonian Monte Carlo, on the other hand, I get a nice looking uncertainty bound that is centered around the true function. And ideally, I would like my uncertainties to be well calibrated in that way. If I take this VIHMC, this hybrid approach, what I see is that I'm no longer in this really poor estimate of uncertainty, but I'm also not quite at the Hamiltonian Monte Carlo, but I'm much better than I was. So using a much smaller number of parameters, I can push myself closer to having good uncertainty estimates. Now we took this and we applied this in the context of a hypersonic flow application where we're looking at hypersonic flow over a cone. And we have here inflow conditions that are represented by the energy spectrum, 52-dimensional input space, and we're trying to predict the pressure at 4 locations on this on the nose cone of this vehicle. And here we're going to set up a Bayesian depot net with this VIHMC approach to quantify uncertainty in the pressure measurements that the model predicts. So when we look at this, what we see here is on the left you have a graph of the parameter sensitivities. So you can see this is in log scale. So we have a lot of non-sensitive parameters. If we actually break this down, our depot net has 16,321 parameters. If we set a variance threshold of 0.9, we actually can reduce that down and only need to quantify uncertainty in 840 of those parameters. So we're achieving a tremendous savings. And this allows us to then do Hamiltonian Monte Carlo on those 840 parameters. Here's just a look at what the VI and the VIHMC look like. The VIHMC, long story short, I won't get into the details here. The long story short is that the VIHMC uncertainties are actually much better calibrated, and you can find more details in the paper that we just published on this, where we introduced the VIHMC approach and to accelerate Hamiltonian Monte Carlo for neural operators. We've taken this approach now to a bigger model where we have now a Fourier neural operator. So this is a Bayesian Fourier neural operator where we're going to be solving a problem in seismic engineering where we have a 6-story structure, highly nonlinear material model, Giuffre Pinto model with random ground motion excitation, right? So these ground motion excitations are filtered white noise based on a target power spectrum that's centered around the Loma Prieta region. And so, excuse me, we took this Bayesian FNO. We built a Bayesian FNO with about 6 million parameters and applied this VI-HMC approach. Now these are fresh results. I don't have the full results. These are very preliminary, But there's an important point here that this Bayesian FNO has about 6 million parameters. You can see the loss that I train using VI. Now you can see the ground motion at each of these, the predicted ground motion at each respective floor, the second, third, fourth, etc. floor. You can see that we now have uncertainty bounds around those, the standard deviation around those predictions. And importantly here, we do this by parameterizing, or I should say quantifying uncertainty in only 8,000 of those 6 million parameters. So performing Hamiltonian Monte Carlo is actually tractable for 8,000 parameters. It is not tractable for 6 million parameters. So all of this is to say that we are pushing in the direction of being able to quantify uncertainty in very large models, right? So we have these very large foundation models, and we want to quantify uncertainty in them. And in order to do that, we have to really be very careful about how we break down the uncertainties and target those uncertainties that are important, because these are huge models. And if we're clever, we can use things like VI and HMC to scale Bayesian methods. We've pushed these now to millions of parameters, right? This Bayesian FNO had 6 million parameters. And we have a strategy now that we think will lead us to being able to quantify uncertainty in these really large foundation models with billions of parameters. I should mention that vanilla VI, things like Bayes by backprop, have already actually been applied in the context of large language models. There are a couple references here that show those approaches. I think we can actually do better in scientific machine learning with these type of approaches. I know I'm getting toward the end of my time, so I'm going to skip very quickly through this second part, and I'm going to focus on really two quick things. Now we're going to talk about scientific machine learning for uncertainty quantification. So in uncertainty quantification, previously we were talking about UQ in scientific machine learning models. I want to change directions and talk about how we can use scientific machine learning for uncertainty quantification. And in particular, I want to talk about how we do it with stochastic models. All right, so these are sort of how we can use vanilla methods for stochastic problems. If you're interested, we just published a paper on neural operators for stochastic modeling for natural hazard applications. These are, again, very large models and for stochastic systems. But I want to really focus on one final development, and that is when we consider a general stochastic problem, right? So we have a stochastic PDE of this form. Well, the classical approach is to approach this with a spectral stochastic methods, right? So we take the solution, we do a spectral expansion of that solution, and this is done with what we commonly refer to as a polynomial chaos expansion, right? And so using this polynomial chaos expansion, we can perform a Galerkin projection, and then we can solve the system using numerical methods. These are your classic spectral stochastic finite element methods and things like that. More commonly now, PCE is used for in a data-driven setting for regression and for surrogate modeling. And we can do this in a non-intrusive way. And actually, Bruno Sudre and his group showed how this can be done in a data-driven machine learning setting. But there are some things that we can learn from this for neural networks and neural operators. So we're going to start with this idea that we need, orthogonality is key to these spectral expansions. And what they do for uncertainty quantification, of course, they enable the Galerkin projection in the classical approaches. But in UQ, what they do is they allow us to directly estimate things like moments, variance, higher order moments, fractional moments, sensitivity indices, etc., directly from the expansion. So what we can actually do is we can actually set up a neural operator using a spectral expansion. And I don't have a lot of time, I don't have much time to get into this, so I'm gonna glance over this very quickly. But if you imagine that I take my operator and I build it out in this expansion form, this is not too dissimilar actually from the universal approximation theorem, this branch and trunk net scheme. What we can do is we can actually build this basis using orthogonal polynomials. same way we do for a polynomial chaos expansion. And we can actually do operator learning with polynomial chaos expansions. And so this is a paper that we just put up on arXiv maybe a month ago, where we show that performing operator learning with polynomial chaos expansions is incredibly efficient. In fact, what you can do is, rather than solving a really complex non-convex optimization problem, for linear problems, you can actually reduce the solution to a simple linear solve. And for nonlinear problems, you can actually reduce the problem to a system of nonlinear equations that you can solve with classical methods like Newton-Raphson iterations. You can also do this in the context of physics-informed polynomial chaos expansions. And the last thing that I'll talk about here is this idea that we can take this now, the same idea, and we can build it up using neural networks. So we can take that same framework and we can build it up using neural networks, where now we're going to take the trunk net and we're going to expand the trunk net so it covers the space of our random variables. Now, this is, of course, just a straightforward stochastic extension of the depot net. It's a somewhat naive approach because now we don't enforce that orthogonality that we wanted, that was so important for us. And so actually there's a way that we can enforce that orthogonality. And I recognize that I'm out of time, so I'm not going to be able to talk about how we enforce that orthogonality, but the basic idea is that in the neural operator, we actually apply the spectral expansion, and then we enforce that the trunk net has orthogonal neural network basis functions. And when we do that, we develop this method that we call neural chaos, or spectral stochastic neural operators. And spectral stochastic neural operators are a variation of these neural operators that have all of the orthogonality properties that we wanted in a spectral expansion, so we can do moment estimation and all of these nice things directly from the expansion, and all of these really interesting uncertainty quantification things in the context of operator learning. So I do want to leave time for questions, so I'm going to skip through the applications here at the end. We have again applied this in the context of a large seismic application. And with that, I am going to conclude, and I want to again thank the organizers for inviting me. This has been really a privilege to talk to you all today. I want to thank the many members of my group who contributed to this, and my many collaborators who contributed to this work, and also again thank the sponsors of this work for their support. And thank you all for attending, and I'd be happy to take some questions.
Thank you very much, Michael. This was a great presentation, and I would like to ask first to the member of the panel of this machine learning school to ask the first question. Then I will have time to collect the questions from the audience. There are several of those, which I will synthesize to Michael after the first round of questions. So I guess Professor Giuseppe Quaranta wanted to start with a few questions, or a question at least.
Yeah, yes, a couple of questions for you, Michael. First of all, thank you. Really exciting presentation. So my first question is about the interpretability of your neural networks. I mean, is there any way to identify which factors contribute most to the final uncertainties using your approach, your models? I'm referring to the integral you showed us, where there are a lot of contributions. Is there any way at the end to understand which factor is most contributing to the final uncertainties?
Yeah, that's a terrific question. And so, this long integral incorporates many different types of uncertainties, and actually the reason that we write this out in this full form like that is because we want to understand the influence of each of these uncertainties, right? So when we think about tokenization, for example, which I'm showing here, we want to be able to zero in and understand the influence of how we discretize on this integral. And so what I've shown here is really focused on the parametric uncertainty in the neural network itself. But there are all of these other factors that come in, and we're we're trying to break this down so we can look at each of these individual factors by themselves, and understand each of their contributions. Maybe a better example of this is the case that I showed where we did the ensembling, where we had model uncertainty through those ensembles. And so you can now get a sense of how that ensemble of models contributes to the uncertainty, which models are good, which models are not so good, and how those factor into the uncertainty of the overall. We haven't done similar things for tokenization or for training strategy, but that is ultimately our goal, is to be able to do that. So can I say we've done it? No, I can't say we've done it. But I think identifying and setting and formulating the problem by breaking it down in this way is the strategy that's going to allow us to hopefully be able to do that.
Okay, thank you. I agree with you. I think that it will be a very nice result if it will be possible to have a clear understanding of all of the role of all the uncertainties involved in that interrupt. Would be a very nice result.
That's certainly what we hope for.
I have a second question, if I may, Marco. I'm referring to the problem where you showed us the stress field reconstruction of a material with internal texture or microstructure.
Yes.
I would like to ask you, Michael, how accurate is the prediction in case of irregular domains? For example, if I'm considering a carved shape, or if there are some discontinuities within the domain, for example, due to cracks. Is the reconstruction still good in such cases?
Yeah, so we haven't looked at cases like that. I think in order to do those sort of problems, we need to apply, first of all, more sophisticated models. A model like this vanilla sort of Bayesian U-net type of approach is not going to get us there. We're going to need some sort of neural
imagine
operator.
that there is a crack, for example, crack.
Yeah.
Yes, in this texture. Imagine that we have a cracks. Do you think that the results will be accurate also in this case?
For this model, no.
No.
For this model, okay. No, it would not work for those applications. We would need to go to a more advanced model that incorporates problems like an architecture like a neural operator to begin with. This is just a neural network, but also you would need something that alleviates your dependence on the geometry and the discretization. So when we go to methods like the resolution independent neural operator, we have some preliminary results that show that we can do predictions using those models for arbitrary geometries. So we can take, we can put voids. Okay. We can put voids of arbitrary random shape in here, and we can handle those type of
arbitrary shape, but not discontinuities. For example, due to cracks. Also, that
there is work using depot nets for crack problems, but anytime you introduce discontinuities, of course, those become really difficult to handle.
Great.
Thank you. I stop here.
Great. So maybe it's better if we alternate questions. So I will pick up some random questions. Well, I pre-select some questions from the audience. I will also remind Michael and the rest of the audience that we cannot go over all the questions because there are a few of them, but they will remain there in Cassini. So if Michael or somebody from his group would like to address some questions, some are quite detailed, and then they will find that they can reply after this presentation. So don't worry, whatever you write will remain there, and we will try to take care. So I would like to take.
I will make an effort after this to look at each of those questions and try to address them the best I can.
That's great, and we thank you so much for this. Let me pick this question by Luigi Caglio. Could you spend some words on how the prior distribution of the parameters in a Bayesian neural network are defined, and how this does or does not reflect our prior knowledge on the problem at hand?
Yeah, that's a fantastic question. Actually, I spent last February. I was in a conference in Canada where we were discussing UQ and neural networks specifically, and this topic of priors was really central to the discussion. Um, I would say a few things. So first of all, the way that we handle priors right now is quite naive. And I'll be the first to admit it, and I'll be the first to say it. You know, we handle our priors in a pretty naive way. I think there are one of the areas where there is tremendous room for improvement here is in the priors, and I would point you to a couple of works or a couple of works that are really interesting in this area from one from Audrey Olivier at the University of Southern California, where she is looking at what are called functional priors, where the idea is that, you know, when I define a prior in a neural network, I'm defining it in some arbitrary parameter space, right? So this arbitrary high dimensional parameter space that I can't physically interpret, you know, Giuseppe, to get to your point of interpretability, right? What I really want to do, if I had my choice, is I'd define the prior directly on the output, right? I'd define the prior on the solution, and then based on that prior on the solution, I'd learn, what does it mean? What does the prior on the solution mean for my neural network? And that's what this idea of functional priors aims to do, is it says, let me define a prior on my solution. And that prior then can be physics informed. It can know the constraints that your solution must satisfy. And then I can take that prior and use that prior to infer a prior on the parameters of my neural network. And I think that's a really promising approach. So I guess to answer the question right now, what the general state of the art is pretty naive, but I think there's a lot of really interesting work that can advance that.
Great. That was a very nice also pick for me. So next question, I would like to pass the ball to Marco Rosso from the panel.
Thank you, Marco, and thank you very much, Professor Schill, for very interesting presentation. So I have a more related curiosity about probably a philosophical question, because my question is related to when and how the networks learn uncertainty. What I mean is when and if there are effects in the uncertainty quantification process provided online during the training phases, or if there are also some effects and we can quantify the uncertainty quantification after a deterministic training phase, and therefore in a post-processing way, and how we can quantify and separating this kind of aleatority and epistemic quantity. Thank you.
Yeah, again, another great question. So there are different philosophies, right, to approaching uncertainty quantification in neural networks. You know, the one that I've more or less adopted here is this Bayesian approach, where we're trying to get at the various uncertainties in the model and in all of the components that break down the model. But there's also questions associated, you know, there's philosophies that look at it as, okay, I'm given a model, right? This is my model. How do I quantify the uncertainty based on that model? And there's some really interesting work in the large language model literature related to that, right? Because these large language models are so big that you can't afford to do deep ensembles and things like that, or even Bayesian approaches. So they're really faced with the question of, I have an existing model. How do I quantify uncertainty? And then they use things like, you know, the mixture of experts and various approaches that allow you to take the predictions that are made and incorporate some aspects of expert judgment and things like that into the training process. I'm not as familiar with those approaches, to be completely honest with you, but there is a substantial body of work around there, and if you're interested, I can point you to a couple of papers that talk about that.
Yeah, thank you. It will be very useful. Thank you very much.
Thank you.
So thank you very much. So I would like then maybe to take a last question. Otherwise, Michael, we need to stay here until this evening, European, maybe American evening, so Italian night. But so let me first apologize with the many questions that I received, but I have some of them are very detailed and long questions, so that it will take a little bit of time here, and then I'm sure that. In Cassini, they will find a better place where there can be post also some references. And I will pick then the last question from Sotiros Dimitriadis. And okay, let me anticipate you received a lot of congratulations, which I skip for the sake of time, but it's good that you know. And he said, my questions are simple. Which is the most computationally demanding and difficult to scale step when using hybrid VI Hamiltonian Monte Carlo? When running sensitivity analysis for parameters, how is hyperparameter tuning done? And finally, can your approach be better than application specific pin? Okay, better the first two questions, then maybe you can say something about the last one.
Sorry, can you repeat the first question?
Yes, the question is which is the most computationally demanding and difficult to scale up step when using hybrid VI Hamiltonian Monte Carlo variational.
So in the VI-HMC approach, so the VI happens on the full model, so that's that comes at the cost of a traditional variational inference approach, and that's of course going to scale with the size of your model, right? So those are the VI approaches. You're usually they're more expensive than traditional training, but they're not usually prohibitively expensive. The sensitivity computation is actually quite cheap. We can do all of that with automatic differentiation. So the sensitivities are not terrible to compute. The really expensive part is Hamiltonian Monte Carlo. Even once you've reduced the parameter space, you reduce the parameter space by orders of magnitude, Hamiltonian Monte Carlo is still going to be very expensive. And so the ability to perform Hamiltonian Monte Carlo and run Hamiltonian Monte Carlo for a sufficiently long number of time and develop and estimate a number, generate enough samples is really going to be very expensive. So it's still a very expensive process in the end, at the HMC step, I should say. And then what was the second question? Sorry.
It was related. When running sensitivity analysis for a parameter, how is hyperparameter tuning done?
So the parameter tuning, so again, you just do the traditional VI, so you identify the parameters, and then to get the sensitivities, we just take the gradients of those parameters around the training points. So you just average the gradients, and whichever parameters contribute most to that approximation of the variance are the ones that you keep for your Hamiltonian Monte Carlo. So I hope that answers the question.
Yes. So for the sake of time, I would like to, first of all, thank you very much. I want to share with you, Mike, for the audience, that this seminar, like the previous one, was quite of a success. We had a peak of around 270 attendees, with an average estimated by my rule of thumb about 260. So
Wow.
that was, yes. So I'm very happy that we had this kind of response. I apologize again for the audience for the number of questions. I still remind you that your questions are not lost. There will be available in Cassini, and I am sure that also Cristoforo and maybe Ilaria and myself had a lot of questions, but I would like to conclude it here, and I would like then to remind the audience of the next seminar. So let me for a second share again the final Okay, continue to share. Here we are. The next speaker will be Kate Wharton on October 29, always at the same time, and this seminar will be chaired by Ilaria. So, Venanzi. So, if there are no any other questions from the panel, or if I have forgot something, I kindly ask to the panel to remind what I just forgot. Otherwise, I would like to say one more time, thank you to Professor Michael Shield, and of course, I hope to see you soon in person somewhere.
Absolutely. And I thank you again for this wonderful opportunity. This was really great. Thank you so much.
Thank you very much, and big hello to all the
Again, Michael,
panel.
really appreciate
panel.
it.
Thank you. Thank you.
Yeah, thank you
Thank
very
you
much.
Thank you very much.
Thank you very much.
Bye,
E tu
everyone.
all the audience.
Bye.
Thank you.